Okay, last talk for today is Pierrick Bousseau from University of Georgia. The title is here, DT invariants and holomorphic flows.
Yes, so thank you very much for the invitation to speak at this conference. So in this talk, I will speak about a relation between two topics. The first one is Donaldson-Thomas invariants for Calabi-Yau three-fourths, the remainder for non-compact Calabi-Yau three-fourths. So it's about counting stable current sheaves, or more generally, objects in the derived category of current sheaves, the Calabi-Yau three-fold X, or the mirror version of this counting problem, which is counting special Lagrangians and manifold of the Calabi-Yau three-fold. So this is the first topic, DT invariants, Donaldson-Thomas invariants of Calabi-Yau three-fourths. And the second topic is holomorphic curves in an Applied manifold M. And the basic relation between these two geometries N and M, you can state it in terms of physics. Starting from the Calabi-Yau three-fold X, you can consider type 2A or type 2B string theory on the 10-dimensional spacetime, which is a product of X with R4. And we'll get in the non-compact R4 a 4-dimensional theory with n equal to supersymmetry. And then the Applied manifold M will be the Coulomb branch of this theory, compactified on a circle. So it fits into these themes. We have in many other talks discussions of Coulomb branch. Here's an example. And here, because this thing actually comes from something in 4 dimension, it has extra structure, and it's a structure of integrable system. And this integrable system is a so-called Savary-Witten integral system in the context of n equal to 4-dimensional series. Okay, so the plan of my talk is first of all to review the kind of general expected picture, for example, following Kontsevich and Soibelman papers of 10 years ago. And then the main content of this talk will be a concrete example where the threefold, the Calabi-Yau threefold will be a very specific one, will be local P2. So the total space of canonical line model O minus 3 of P2. So this thing will be our non-compact Calabi-Yau threefold. And then the Applied geometry, where we'll consider holomorphic curves, M has different incarnations depending on which complex structures you look at. And in some complex structure called I, this thing will be some elliptic fibration. So in this example, M will be simply of complex dimension 2, real dimension 4. But in some different complex structures, it will have different realization. In so-called complex structure J, it will be some affine algebraic variety, which will be simply the complement of a smooth cubic curve inside the projective plane P2. And from the kind of Applied geometry point of view, this geometry has a so-called ALH star metric, which has been recently of interest in differential geometry. And at the end of the talk, I will mention some kind of heuristic and physics derivation of the general correspondence and mention the relation with holomorphic flow theory. Okay, so I start by the kind of overview of the general expectation of the general topic. So DT invariants are denoted like that, omega gamma of U. So they are integers and they are count of geometric objects on the Calabi-Yau threefold X. And so they are indexed by some class gamma, which is roughly the topological class of the object. And they are also indexed by this parameter U, which is a stability condition. So typically a Bridgeland stability condition in your category of derived category of current sheaves or Fourier category of X. And omega gamma of U is in some sense a count of stable objects with respect to this particular stability parameter. Okay, so here I mentioned the two examples. You might count things like stable holomorphic vector models of current sheaves of given chain character gamma, where the stability is determined by a Keller parameter U. Or you can consider the mirror version, where you're counting special Lagrangian submanifolds of given homological class gamma, where the stability is determined by a complex parameter U. Here is some kind of physics translation of DT theory. So if you have a 4-dimensional field theory, which has so-called n equal to supersymmetry, then attached to it is a Keller manifold B, which is called the Coulomb branch of vector of this four-dimensional series. And then the point U of the previous slide should be a point in this geometry, more precisely a point in the complement of some discriminant locus delta. And physically, at such a point, at such a vector mode theory, you have an abelian gauge theory with gauge to U1 to the R, where R is an integer for the rank of the theory. And then in such a theory, for such choice of vector mu, and for choice of charge gamma, you have a notion of BPS states and of space of BPS states. So I'm denoting by H gamma of U the space of BPS states, and then you get some BPS index, which is roughly the dimension of the space of BPS states. Okay, so this thing is just some physics context where you also get number omega gamma of U. And related to the previous geometric word of DT invariance, if you start with type 2 of type 2B string theory, you compactify the Calabi-Yau threefold, and you will get an example of such four-dimensional supersymmetric theory. And the general expectation is that the universal cover of his Coulomb branch B of this four-dimensional theory should have a natural map to the space of Bridge-on stability conditions on the category you care about in your Calabi-Yau threefold. And then the DT invariance omega gamma of U for stability condition U should be equal to the count of BPS states for the corresponding point on the Coulomb. Okay, so the basic property of this DT invariance omega gamma of U is that they are locally constant as a function of U away from codimension 1 loci in V called walls, but across these walls they can jump discontinuously. So this is a wall crossing phenomenon, which is controlled by universal wall crossing formula due to a Kontsevich and Soibelman. So this thing is like the first part of the relation. On one side, you have this kind of geometric Calabi-Yau threefold. On it, you can consider either current sheaves or special Lagrangians. You will expect it to be able to extract some numbers, some DT invariants, which satisfy this wall crossing formula. So the second side of the story involves this hyperkähler geometry, which in the physics context is a so-called Sylberg-Witten integrable system for the four-dimensional theory. So which is physically realized as a Coulomb branch of the theory compactified on a circle. So it is an hyperkähler manifold of complex dimension 2R, where previously R was the rank of the theory. And it has a natural structure of complex integral system. So it has a natural map to the Coulomb branch of the theory on R4, B. And it has a property. So one way to explain what this geometry is doing is that if you start with a four-dimensional theory, and if you compactify it on a circle, and at low energy, the circle looks very small, and what you get is a three-dimensional sigma model which targets this hyperkähler manifold. Okay, so it is hyperkähler, so it has a twisted sphere of complex structures, by IJK, some quaternionic triple of compatible complex structures. And sigma pi from M to B is a complex integral system. So it's holomorphic in a particular complex structure that I denote by I. And the generic fibers of this map are abelian varieties of complex dimension R. And for every ongoing theta, generic fibers of pi are special Lagrangians with respect to the Kähler forms, with respect to the complex structure J theta, where J theta is a linear combination of J and K with coefficient cosine of theta and sine of theta. Okay, so the general picture is that you have some kind of torus fibration. In some complex structure I, it's a holomorphic fibration, but for any theta, it is actually special Lagrangian with respect to the Kähler structure in complex structure J of theta. And furthermore, this hyperkähler geometry encodes some of the data which appear on the DT side or BPS side, in particular the set of possible classes or charges gamma for your DT invariance of your BPS states can naturally be identified with the relative pi2 of M relatively to fiber of this map pi. Okay, so here is a very basic picture of a complex integrable system. You have a torus vibration over some base with some singular fibers in complex dimension. And a typical example of such picture is also called the class S series. This thing is essentially some I-Ching integrable system. Okay, so I've very briefly described the two sides of the story. One side involving this DT invariance omega gamma of u, and the other side, which is this complex integral system curly L. And the general, maybe slightly vague expectation is that there should be a relation between, on one side, omega gamma of u, which has DT or DPS invariance counting u stable objects of class gamma on one side. And on the other hand, what I denote by L gamma of u, which would be something like count of J of scalar holomorphic disk in this holomorphic hyperkähler geometry M, with boundary on the torus fiber pi inverse of u and of class gamma. Whereas the specific angle theta to choose is determined. It is somehow fixed by the geometry. It has to be the phase of the central charge, that gamma of u, while the central charge is determined by the periods of the holomorphic symplectic form omega I. Okay, so on the two sides of this equality, the various things have very different meanings. So on the left-hand side, the u parameter is a stability parameter on the DT side, whereas on the right-hand side, the u is like really specifying a torus fiber in this torus vibration. And then omega gamma q is the count of stable objects in the Calabi-Yau 3 category, branches of the category of the Calabi-Yau 3 fold, whereas the right-hand side is about counting holomorphic curve. This is torus vibration. And so remark, we count holomorphic curves in the complex structure for which the torus fibers are special Lagrangians, for which somehow it makes sense as nice boundary condition for counting holomorphic curves, not the complex structure for which this vibration is holomorphic. So here is a list of some more evidence for why you should expect to have such a correspondence or such relation, because it's two very different looking things. So one piece of evidence is, for example, this work of Bertun-Wojnarski, which explains from a physics point of view from the BPS state, so the DT invariance, how you should be able to reconstruct the hyperkähler geometry of M. So this thing is like on the DT side, whereas on the holomorphic curve side, these holomorphic curves or holomorphic disks are exactly the so-called instantons of quantum corrections that you are supposed to use to construct the mirror of such geometry, where the torus vibration appear as a SYZ torus vibration. And somehow the main piece of evidence is that in both cases, there is a kind of wall crossing formula, wall crossing structure. I'll show you to Kontsevich and Soibelman in both cases. And the main observation is the Kontsevich and Soibelman paper, that is two wall crossing structure looks very much the same, and so you might expect them to be related. And even more precisely, Kontsevich and Soibelman explained that you might expect to have some kind of third intermediate objects between these two things. You might expect going from holomorphic curves to tropical curves in the base of this torus vibration. And then this kind of tropical curve in the base of the torus vibration should have some interpretation on the DT side in terms of so-called attractor trees. Here's a kind of very basic picture. You have this holomorphic disk in this torus vibration. In some appropriate tropical limits, they become trees on the base. And then you might expand these trees to have some meaning on the DT side as moving inside the space of static conditions in some specific ways. Yes, sure. Yeah, that's all. So yeah, in the case where your series of class X, so is whatever number, the DT invariant should also be captured by the spectral network of everything more. Is it what you are meaning, or? Yeah, so here I think what I'm discussing is different, and I think it's not obvious somehow. So it's like something which is maybe sounds similar, but which is different, is that for some of these spectral network, I think that projectional holomorphic curve, but it's a cotangent bundle to the curve. Where here we are looking at a curve really inside the total space of this torus operation. And so in some kind of ways, there are some of like two orthogonal things, and so I will not say more about the relation. Okay, so to make this kind of picture precise, there are several issues. One of them is that the embedding of this base P of this torus operation in the space of Brillouin static conditions is not known in general. And the related issue is that in general it's quite difficult to make sense of count of holomorphic disks. So it's related to the general problem of counting holomorphic disks for mirror symmetry. And so in the example I will explain, so for the second issue of counting holomorphic disk, we will use some kind of algebra or geometric replacement for them given by a so-called logarithmic homological invariants, which have been introduced by Gross and Siebert exactly in this kind of with this kind of mirror symmetry motivation in mind. You know, some kind of XYZ torus operation. When you try to look up the mirror, you need to somehow count this holomorphic disk. And what Gross and Siebert are doing algebrogeometrically is to replace this count of algebrogeometric disk by these log Homological invariants. In the kind of concrete example I will describe, it is what I will do. Yes. Yes. So actually, yes. Yeah. So maybe in general, it's not clear. So for example, if you start with the abstract n equal to 4D theory, maybe you don't know if there is a Calabi-Yau 3 attached to it. Yeah. So let me say that in general, it's not known how to construct that. Maybe if you want after the talk, you can ask me again and I can say something more. Yeah, so in the example, I will consider there will be a Calabi-Yau 3 to start with this question. Okay, so it is how we go somehow in our example. I will go around this problem. We use log Homological invariance. So there may be other approaches. So we might use like non-Archimedean geometry to count this disk. Here we'll use this Gross-Siebert log Homological theory. Okay, so somehow as an example of this general expectation, somehow the talk of Julia's yesterday, which was some relation between DT invariants of Fourier's potentials and log Homological invariance of toric varieties and cluster varieties, is some kind of example of this relation in some kind of limit where the space of parameters have some kind of like space of stability parameters as a nice description in terms of the quiver, and the limit for some of the singularities of the integral system are sent to infinity. So in this talk, I will only consider a very specific example, which is different from this one. So as I announced at the beginning, we'll consider DT invariants for current sheaves on this non-compact Calabi-Yau which is local to 2. And so why I'm focusing on this example, it is actually one of the rare geometric example where it is actually known that the space B, this kind of Coulomb branch of the physical theory, is one of the few cases where it's known how to embed this space into the space of Brillouin stability conditions, and for which you can even start to make precise this picture. Okay. Are there any questions on this like first part, which is like quite general, and then I will start being more specific about considering a specific geometry. Yes.
Question about these pictures, maybe I'll explain them. But so I understand these tropical pictures in the base, why they are supposed to encode holomorphic curves.
Yes.
But what's the meaning in the sort of in the stability condition? Like, what's the meaning of a straight line in the space of the stability condition?
Yeah. So it's related to these abstracted trees, and maybe one way to describe them is in terms of saying that there are gradient flow lines for the absolute value of this total charge. So for in DT theory, that is total charge, and somehow you want to somehow very rapidly this attractor picture, you want to decrease the absolute value of this object. So in the kind of geometric spatial Lagrangian, the setup this absolute value is the volume of spatial Lagrangian, and you try to decrease this volume. And so you might try to do that following some gradient flow tree with respect to a natural metric on B. Actually, in the physics setup, there is really a metric, and so you can try to move along the corresponding gradient flow.
Great.
And in the example we'll describe, because it will be some kind of low-dimensional example, I would say even more precisely than what's there.
But now you only have gauge theory, but you don't have parameters. Then what does this formalism mean?
Yeah, so it's true that in the physics story, the attractor picture comes from the supergravity context, but the claim is that so in this example, even if there is no gravity, the claim that DT invariance will still be captured by saying it looks like attractor trees.
Yeah, so, but the physical meaning is not very clear.
Yeah, that's right. Maybe then the physical meaning is not so clear.
Thanks.
Okay, so the precise setup I'm denoting by X. KP2, the total space of the canonical line bundle, O minus 3 of P2. So this thing is a nice example of non-compact Calabi-Yau threefold. And inside it, you have the compact projective plane, P2, which is naturally embedded in X as a zero section. And here the category we consider is D P2 of X, the bounded Dirac category of current sheaves on X, which are set-theoretically supported on P2. They are current sheaves on this non-compact Calabi-Yau threefold, but somehow they live near the zero section. And in particular, if you have a sheaf on P2, you can view it as an object. You see it's a category, they are pushed forward by the zero section. And when I use the notation O of n, I really mean the line bundle of n on P2 is supported on the zero section. In physics language, it's a P4 word. Okay, so this thing is a non-compact Calabi-Yau threefold. And then you can start trying to run the general description I explained to you. If you compactify that two-way string theory on this non-compact Calabi-Yau threefold, you get four-dimensional theory. And so on the other side of the story, what you need to do is find a Newton geometry of this particular four-dimensional theory. And so the first question is what is it? And the claim is that it has a particular simple explicit description that can be related to mirror symmetry. So first of all, there's a four-dimensional Floer branch B, so which would be the base of our torus vibration, minus the discriminant locus will have an explicit description as a modular curve. So this base will be complex dimension 1, and it will be the quotient of the upper half plane by an explicit congruence, a subgroup of SL2Z, which is gamma 1 and 3. And then the corresponding torus vibration of it will be simply the universal family of elliptic curves over this modular. So it's a very explicit geometry. So here's a picture of the fundamental domain of gamma 1 and 3. And so you can look at the quotient, I get a modular curve. So if you compactify it, it's really a sphere. And but actually what is missing is a point at the top here, which is the so-called large volume point. And the other missing point at the bottom is the polygon point. And in addition, on this picture, there's a special point in the middle, which is called orbital point, where there is a Z03 Z orbital. And actually, just to get rid of the orbital point, it will be technically easier to work on just 3-to-1 cover of this picture where you resolve the orbital point. And so we denote that B prime is 3-to-1 cover. So B prime as a complex manifold is just a copy of the complex plane. And there is three conical points on it. So before there was a single conical point, now there is three of them because I took a 3-to-1 cover. And then over this geometry of the pullback of the universal family of elliptic curve, that is denoted by n prime. So away from the conical point, it's a smooth vibration in elliptic curves. And at the above the 3 conical points, I only get 3 nodal singularities, 3 nodal elliptic curves. Okay, so this thing will be our applied geometry, M or M prime, and this thing will be our complex integrable system or torus vibration.
Can you say
Yes.
which Hitchin system this corresponds to?
Yeah, so I don't think it is a Hitchin system because it's some kind of more, maybe in some sense, this 4D theory is more kind of 5D theory on a circle. So yeah, another way to say it is that, like in Hitchin system, like if you think about the most natural analogous spectral curve in this setup, it's really some curve in like C star squared, not in T star of a Riemann surface. It's some kind of trigonometric curve. So I don't think it is on the nose of Hitchin system.
It's not in the go-out list. No. No, never mind the work which Hitchin system.
Yeah, I'm pretty sure it's not a Hitchin system, and we can talk about Borch list. It's compatible with whatever is in Borch list. So yeah, Borch lists are things which are not Hitchin system, but which are like a trigonometric, and this thing is an example.
Oh, you think it's in Borch?
Yeah, so this example is a bit away from more traditional Hitchin system, but it looks very much the same. Okay, so now for this very particular example, I told you what is the Calabi-Yau threefold. I told you what is the integral system. So now I want to explain on each side what are the DT invariants and what are the homological curves. Okay, so on the DT side, we consider the Dirac category of current sheaves on the non-compact Calabi-Yau threefold, and we consider the spaces of static conditions on it in the sense of Bridgeland. And here, the thing which is known in for this geometry, and maybe not in many other cases, is that the universal cover of the base of this integral system, indeed, as is expected, as a natural map to the space of Bridgeland static conditions, where this map is somehow the one expected from a mirror symmetry. For example, this central charge Z is really given by the periods of this homological symplectic forms. Okay, so as a result of my back tree, you can really consider any point on the base, or more precisely, any point on the upper half plane, which is a universal cover, really as a Bridgeland static condition on your Dirac category. And so in particular, for any point tau in the upper half plane, you can really do DT theory. You can introduce moduli space of tau, stable or semi-stable objects, and then define DT or PPS invariants counting these tau stable objects. And so here the wall crossing appears as a function of this point tau in the upper half plane. Here I have some slides which have some just saying what happens at a very specific point. So on the base B, there is a very specific point which is an orbifold point. And as an orbifold point, the kind of Bridgeland static condition is a description in terms of some category of representation of Floer with potential, which is a kind of standard Floer with potential attached with this local P2 geometry, which is quiver kind of Markov like quiver with 3 vertices and 3 arrows in this cyclic way. Okay, and so the first thing I want to explain is how to describe these DT invariants as flow trees or attractor trees in the upper half plane, the universal cover of the space. And as I already mentioned, this thing is kind of motivated by the gravity attractor picture. or the general expectation due to Kontsevich-Soibelman that you should have a nice wall crossing structure and base of complex integrals. So what do we do precisely? We fix an angle theta, and then for every class gamma, so maybe I should have been more precise. So here gamma is really some kind of chunk character for the current shifts. Here in our geometry local P2, the chunk character just leaving a lattice of rank 3. It's like we can rank degree and second chunk class. So gamma is just a triple of 3 integers. And so for every choice of gamma and every choice of angle theta, I will look to some locus in the upper half plane R gamma plus of theta, which are the points in the upper half plane where the central charge that gamma has a specific phase theta, and where you have a non-zero DT invariant of class gamma for the stability point tau. And on the picture, I will orient the rays so that the absolute value of the central charge increases. Okay, so this thing is a completely precise definition. Okay, and then you can start drawing the upper half plane and try to draw what are these sets. So for example, if gamma is a class of the O, so the line bundle on the 0 section P2, and if you ask what is its locus, you can plot it, and it is curved here on the right, starting from the bottom and curving over the left. This is the one associated to the line bundle O. On P2, you can have the same for the line bundle O minus 1, shifted by 1 in the direct category, you get the curved curve on the left. Or you can ask a question for the structure shift of a line in P2. And what you'll find will be some vertical outline stopping at some point, which is exactly the intersecting point of the two previous curved lines. And the claim is that, so you will have this picture. So for every theta, you get a picture, the fixed theta. Then you draw all these loci for all possible classes gamma. And the claim is that if you decorate these rays by essentially the generating series of DT invariants, you get a so-called scattering diagram more structured than in a D of theta. And so what's happening in this picture is that the intersection points of these various rays will be exactly the points where you are on the wall, in the center of the wall crossing for DT invariants. The reason being that if you have two rays intersecting at this point of this picture, it means that the two rays coming, the phase of the central charge is are both equal to theta, because I'm only looking at object of the theta. And so if they meet, it means that at this point, these two different objects, the central charge has the same phase, which is exactly the point where you can have notional wall crossing happening. While the notion of stability can change in notion. Okay, so what is happening in this picture is that, for example, is that if you look at the structure shape of a line in P2, then in the upper part of this picture, the object is stable, the red vertical line. But in the lower part of this picture, this line does not exist because this object is unstable. And what happens is that the structure shift of a line, maybe I should write it here, fits into an obvious exact sequence on P2. On P2, you have the obvious exact sequence. If you have a line, structure shift of a line, it fits into such a short exact sequence. And in the direct categories, we have a channel. And the claim is that in the lower part of the picture, these objects become unstable because this thing becomes a sub-object which destabilizes. And conversely, so the two kind of initial rays coming from the bottom here, they are like corresponding to this object and this object. And then when they come together, they kind of produce this new object, extension of these two things. Okay, so this thing is a basic picture of the wall crossing, but in this example, we see kind of very pictorial illustration. And here, so in the theorem, joint work with Descombes, Floch, and Pioline is that in this example, for every theta, you can somehow describe this scattering diagram d theta in a kind of explicit way. Here I describe it like assuming that you know all the DT invariants, there's a definition, but somebody wants to compute or describe DT invariants. The system will tell you how to produce, to reconstruct the full picture in terms of explicit initial rates coming from conical points, which are the kind of initial points on the horizontal line, and then some of scattering, which is rays come together, some explicit production of new rays according to the Volkowski formula. Okay, so this thing is actually an algorithmic way to reconstruct the full set of DT or BPS environments at any point in this kind of upper half-plane slice in the space of stability condition. And these initial rays have some kind of attached conical points. They have some clear, some kind of explicit description. So essentially, you have conical points corresponding to the line models O of n. So there are conical points where the line model O of n have zero total charge, which is also on the boundary of the space of stability condition. And you have initial rays coming from these points. And you have actually much more general conical points. You can apply limit of gamma 1 or 3 to any one of these conical points, but new conical points where you have spherical objects in your category becoming masses, so with zero horizontal charge. So actually, so in this picture, there will be like infinitely initial points indexed by gamma 1 or 3, which correspond to all the possible spherical objects in your derived category. So maybe I should have made this remark before. So here's this group gamma 1 or 3, which have here the modular curve. From the derived category point of view, it is really realized as a group of autoequivalents of the derived category. And so here is some kind of more complete picture before I will draw a very small piece of the picture, and here is some kind of bigger picture. And as I said, you can draw this picture for every angle theta. And so this is a picture for the angle theta equal pi over 2. And it happens that, for example, if you only care about what happens in the very upper part of the upper half plane, then everything will be produced by initial rays coming from the conical point at integer values 0, 1, -1, and so on, which really correspond to the line models of. And then once these lines come together, you get a non-trivial interaction and you get a more complicated picture. And so, for example, part of the claim that this picture allows you to recover some more kind of classical invariants, which are saying like other characteristics of modi space of Gieseker semi-stable sheaves on the projective plane. And because you can show that if you take your point on the upper half plane very far up, then the Bridge-Jones stability condition reduces in some way to Gieseker stability conditions. So what we is modi spaces and gamma of tau, that tau is very far up, really become modi spaces of Gieseker sheaves, not just objects in the derived category for some abstract Bridge-Jones stability condition. And in particular, if you care about this modi space of sheaves on P2, you can access them starting from the bottom of this picture and then going up in this picture and then on the at the top. So this thing was a picture for pi over 2, but you can draw the picture for any angle you want. And this thing is a picture for theta equal to 0. So this picture looks very much different. So you still have initial things coming from conical points, so here's the red lines coming together. But before they were like first intersecting by pairs, and then there's more and more interactions. Here what's happening is quite different. You have essentially like triples of initial lines, all coming at the orbital point. This is the point here in the middle. And then from this orbital point, you have like blue lines which are confused. But these blue lines never intersect again. They just go to infinity without further intersection. So the qualitative picture is quite different from the previous one. And this thing is an especially nice picture because at the orbital point, as I mentioned before, you have this kind of Fourier distribution. And so this thing is telling you that at least for the invariants which are captured from this picture, you can go from the orbital point, so things captured as Fourier, to infinity up, which are things captured by geometric sheaves on P2 without crossing any walls, without any wall process. So this is some kind of picture of something which actually was known some time ago, that you can tell a direct description of some Molly space of physical symmetrical sheaves and the same appropriate condition are just Molly spaces of Floer representations. But this picture does not give a clear geometric explanation why you just go directly from one to the other. So you restrict the object of a given phase theta equal to 0, and for this object there is no walls between the orbital point and the large volume. Okay, so some of these things was like the DT side. For the DT side, the upper half plane, you can really view it inside the space of regional stability condition. Then you can draw this scattering diagram or Walker d theta for every involved theta. And you can really reconstruct them algorithmically from simple initial data coming from the photos. Here's a picture for pi over 2, and here's a picture for 0. And actually, there is something very interesting happening. Somehow, if you like various theta continuouses of this picture should deform to this picture. And there is a sequence, for example, if you start at pi over 2, and if you deform theta a little bit, just this picture gets deformed, but combinatorially you remain the same. And then there's critical phases where somehow you have jumps in the pictures. And at some point you have some discrete set of jumps and some dense set of jumps. And anyway, we go from this picture to this picture. Now my goal is to describe the holomorphic curve side. So I'm supposed to say something about J theta holomorphic curves in this torus figuration n or n prime. And here, if I want to do that in some kind of explicit way, the first problem I have is to describe this m prime. Okay, I want to count holomorphic curve in it, so I would like to know it relatively explicitly for the relevant complex structure. And until now, I have only told you what is the geometry, what is this torus figuration in the holomorphic structure I. Okay, I described this thing as an algebraic variety is family of the curve. Called I is a complex structure for which this thing is holomorphic. But what I want to count holomorphic curves in is for some more apically rotated version of this complex structure. And in general, if you have a complex manifold which happens to have apically metric, it's somehow non-trivial to know how does the apically rotated complex structure looks like. And here we will be somehow lucky, we'll be able to know it at least for the two specific values, pi over 2 and 0 of theta, and it is the only values for which I would care about. So actually, I mean, from a logical point of view, for the result I will explain later, I don't really need the apically metric business, but somehow to explain how it fits into the general picture, it is useful. And so here I will refer to this recent result of Colin Jacob and Lee, which really studied like complete apically metrics in this geometry and proves the following. So if you consider this apically rotated complex structure J theta, or theta equal pi over 2, your complex integrable system becomes some affine algebraic variety, which is simply the complement of a smooth cubic curve in P2. So just P2 minus an elliptic curve. Okay, so the thing is, because an elliptic curve is anticanonical, P2 minus P is clearly a non-compact holomorphic symplectic surface. But the non-trivial statement is that it fits in the same twistor family as some of our integral system I was describing before. Okay, so it is the first thing we will use for theta equal pi over 2. We know what the geometry is. It is P2 minus 1. And the other thing we'll use is that if theta equal to 0, actually this apically rotated complex structure is isomorphic to the original one. It is still an elliptic fibration, which is maybe a bit surprising. And here it's quite different from what happens in the itching situation. Like often, at least in the simplest itching situation, like for one complex structure, you get some holomorphic fibration, but for all of them, it's not. But here, for even for the apically rotated one, is still holomorphic fibration. And somehow here in the geometry, there is some kind of intricate twin torus figuration structure. There are really kind of two orthogonal torus figuration. And what happened is that for power 2, both of them are special Lagrangian. For I, one of them is homomorphic, the other is special Lagrangian. And for J0, they kind of flip. The special Lagrangian previous becomes homomorphic and this way. But the point is that okay, for theta equal to 0 and theta equal to power 2, we have some kind of algebra geometric description of these two complex manifolds. And so you can use algebra geometric techniques to describe holomorphic curves inside, so that log from of which invariants. And here's some theorem. Is that the picture I was doing before for power 2, which was capturing dt invariance of this power 2. It's actually proving now the correspondence. Is that it's really described tropical curves capturing log curves inside the geometry P2 minus E. So maybe more precisely, algebra geometrically, what we are doing is compactifying P2 minus E as P2 with a divisor E. And what we are really doing is counting rational algebraic curves in P2 with appropriate tangency condition on E. And this thing is your kind of algebra geometric model for holomorphic disk in the complement. And then you can prove that this picture is a correct description of these holomorphic curves. And so as currently you really get from a one precise version of the general expectation, you really get some precise correspondence between dt invariance of this local projective thing of phase power 2 and count of rational curve in P2 minus the elliptic curve. And here it's not something I will talk about much, just to mention that once you have this relation, you can do non-trivial things with it. Once you have related these two very different things, like dt invariance on one side and holomorphic from a foot and path things on the other side, then you can transfer information from one to the other to prove something which is obvious on one side, to prove something which is not obvious on the other side. For example, you can prove this something about Tychowski's conjecture, which is purely about enumerative geometry, or P2 is an elliptic curve, which has nothing to do with either dt or apicular geometry, or which the only proof I know is through this relation. And conversely, you can say non-trivial thing on the dt side, so that modularity properties using the picture. Okay, so this thing was for power 2, and for theta equal to 0, you have a similar result. For theta equal to 0, this picture indeed describes log curves now in the elliptic fibration with complex structure J0. And so as a conclusion, you get again this precise version of the general expectation, you get some correspondence between dt invariance of local P2 of J0, which is an example the same as dt invariance of the quiver with potential, because as I mentioned before, there is no wall. And they're also the same as some count of log curves, rational curves in elliptic fibration and on J0. Okay, so in these two currently, you have some of the kind of explicit realization of the general expectation. We have equality between all the various things which should be equal according to the general expectation, the dt invariance, the kind of curve side, and the capture of the kind of tropical tree picture. Okay, which ends this talk by some kind of more general questions. So the general question is like, why should such correspondence be true? So the general relation between dt invariance of Calabi-Yau threefold and holomorphic curves in the integral systems. So we have this picture somehow which goes through the base, which use like tropical curve or trees, but you can have either some kind of more direct geometric relation between the two. And let me first mention that in the example I've described, somehow you can't come up with such geometric explanation, which is kind of difficult to make precise, but which at least kind of makes sense. So the concrete question is, okay, is it possible to go directly geometrically from current sheaves on local P2 to J theta holomorphic curves in this integral system NP? And the claim is that it should be possible, and it relies on the fact that the mirror of geometry 1 of local P2 is actually very closely related to this apicular geometry N. More precisely, the mirror y of x is a non-compact threefold that you can describe as some affine quadratic bundle over M, which is ramified over a fiber of the first operation. So maybe the most standard description of mirror symmetry for things toric like local P2, people will consider some kind of potential in C star squared, and then we say the mirror will be something like UV equals cis potential in C star squared. And here it's the same actually, except these like fibers of the potential that are really compactified into the integral system. Okay, so why? So the point is that in this very particular example, there is some kind of numerical coincidence that is applied geometry M is very closely related to the mirror Y of X. And then you can do the following path. If you start with holomorphic disk in your integral system, so they are J theta holomorphic, but for the original I complex structure, they're really special Lagrangian. So this holomorphic disk, there are really some kind of special Lagrangian disk with respect to like a Keller structure for which the fibration is holomorphic. And then you can do some standard symplectic operation with these functions. If Lagrangian disk inside the surface M, you can lift them into closed Lagrangian into the three-dimensional geometry Y, precisely because Y, the conic bundle over M, which is ramified on the fiber where the disk has ended. So this disk, so you start with holomorphic disk, they become Lagrangian disk in the surface, and they lift to special Lagrangian in the threefold. And then by mirror symmetry, you expect the special Lagrangian in the threefold Y to be something like Franchi's or object of the Dirac category on the mirror side X. Okay, and then there is a physics version, the secret of string duality, which is a physics version of these geometric operations. Okay, so it's difficult to make that precise because in general it's difficult to find special Lagrangians. When you use this apical rotation, it's not really clear how counting disk in a Gromov-Witten way is related to counting special Lagrangian in a DT way. So I don't know how to use this sequence of arguments into a proof, but still it's some kind of geometric explanation for why you should get such correspondence. But here somehow it's collized with some kind of numerical coincidence that somehow this integral system is like a very low dimension, just surface. And so it's kind of very close to the mirror, which is dimension 3. In physics language, like you can really put this integral system as part of the space-time of a string theory. But in more general situation, your integral system will be something of much higher dimension, which will be very far from dimension 3, so such kind of explanation cannot really hold. So I would just end by a few words about the kind of a general explanation, which unfortunately will be only a physics explanation. And this physics explanation, inside it, I need to mention holomorphic Floer theory, so following Kontsevich and Soibelman. And so here I just very quickly remind, I will go extremely quickly to result that if you have a holomorphic symplectic manifold, so this thing was also mentioned in the Gemesh talk on Monday. So the basic idea of this holomorphic Floer theory picture is that if you have some holomorphic symplectic manifold, if you have two holomorphic holomorphic Lagrangian manifold L1 and L2 inside it, you can consider the space of paths between the twos. And on this space of paths, so it's an infinite dimensional manifold, you can construct some holomorphic function W, essentially by integrating the holomorphic symplectic form. In the same way that in usual Floer theory, you consider some kind of Morse-like function by integrating the infinity symplectic form. Here you get the holomorphic function by integrating the holomorphic symplectic form. And then you have some kind of infinite dimensional non-Gainsbourg model. This space of path P with the holomorphic function W, and then you can try to play the games we play with finite dimensional non-Gainsbourg model in this infinite dimensional setup. And so you get structures like the critical point of this function, which are intersection points of the two Lagrangians, as in usual Floer theory. Gradient flow lines, which will be J theta or the curves. So maybe here I should mention here in this picture, gradient flow lines can consider a real part of W rotated by phase, theta, and then the corresponding gradient flow line are exactly the J theta of the curves that we care about. And here in this picture, if you believe in it, there should be some kind of extra structure which has to do with counting all of the curves in the Descombes point of view, which now is one level up, is counting like marks of R3 to M solution of some Floer equation. And out of all of this data, given two intersection points P and Q, you should be able to attach the vector space H to Q. Okay, so this thing is a bit different. So the usual Floer theory, if you have two intersection points P and Q, you only get a number by counting the polars, then you use these numbers. But here, if everything is one level, categorical level up, you should be able to attach a vector space to a pair of intersection points. And now, how is it? So now I'm back to our original question. So back to some four-dimensional field theory. The original question is why it should be the case that you should be able to recover the VP states of this theory from something like holomorphic curves or holomorphic Floer theory of the associated integrable system. So what I need to describe is, okay, so we know what is the holomorphic symplectic manifold is. It's just this integrable system, complex extra I. And what I need to do is to produce two interesting holomorphic Lagrangians, which somehow will reproduce our previous story. And the two Lagrangians are quite natural. I take for L1 a fiber, the integrable system, which is quite natural because everything in our story depends on the point in the base, which is either stability parameter on the dt side or the fiber on the holomorphic curve side. So I just take this fiber, which is a nice holomorphic Lagrangian. And as other holomorphic Lagrangian, I just take a section. And the claim is that in the physics related, in the physics motivated story, there's an outward choice of section, which is some kind of boundary condition for the 3D sigma model coming from the cigar geometry unfolding and then reducing the circle the two point. And like for things like Itching system, you should agree with things like Itching sections. Okay, so here is a very schematic picture. You have an integral system, you have your torus fiber L1, your section L2, and then you just run Floer theory or holomorphic Floer theory for these two Lagrangians. So here maybe it looks like it will not be interesting because these two things are only one intersection points. But as usual in this kind of context, actually this function is multi-valued. It's actually because torus as a non-trivial fundamental group, so actually the space of path is multi-valued, is non-simply connected, so this functional is multi-valued. So you work on some cover, and on this cover, your single intersection points will lead to some kind of lattice of critical points. It's exactly as in Soibelman's talk on Monday, we have a similar picture of a critical point of Chern-Simons functional. Here is the same picture. And in particular, now the critical points on the cover, they are naturally, so you can show that the fundamental group of the space of path is exactly the correct lattice of charges, whereas this gamma is living. So now the cover, the critical points are already indexed by this classes gamma. And now the kind of conjecture, which is just some kind of like lift of the general expectation. So the general expectation is that the dt invariants are related to count of holomorphic disk. And here it's a kind of lift of this version because after all dt invariants, they're really dimension of some vector space. So they should not just be number, but you should get vector space. Whereas on the holomorphic curve side, it's a bit unusual because in usual Floer theory, counting holomorphic disk, you get numbers, but in general, you don't expect these numbers to lift to vector spaces. But somehow in holomorphic symplectic or arc-Keller situation, because of holomorphic Floer theory, you do expect such. So now the expectation is that if you are at the point 2 in the base, the space of BPS states, H gamma of U, is actually the space attached by our precursor to these two Lagrangians. And when you consider the lift 0 and gamma of this unique region. And somehow you can check somehow it reduces to the first story. There is some very small geometry you need to think about that actually in our precursor for these two Lagrangians, which has what are gradient flow lines because these two Lagrangians, actually they can be naturally be viewed as generated holomorphic disk with the boundary of the choice. And I will just end by some kind of the promised physics derivation. So which is extremely crude. Here, it's only this picture. So I want to explain how to go from BPS states of 4D theory to things like holomorphic first theory of the integral system. And the claim is that if you start with 4D theory, you can put it on this kind of cigar geometry times R2. And so you care about the BPS spectrum in the vacuum U. So at infinity, the thing should be related to U. So it's natural to put as boundary condition here the fiber over U. And then I look to inside this figure all the states of charge gamma. And so like the kind of supersymmetric ground state of the system should be exactly BPS states of charge gamma. But then in this picture, you can reduce a circle to a point. And then you will get a three-dimensional geometry. And by general property, Coulomb branch, it should be a three-dimensional sigma model which target the integral system, and the root integral system. But now the three-dimensional geometry is R2 cross an interval. And now at one side of the interval are the fiber of U. And on the other side of the interval are exactly the section, because this section is exactly what comes from the cigar, the tip of the cigar. And in between, I want something of class gamma. So the claim is that this picture here, actually, if you really look to the theory of R2 here, it will really be the kind of infinite dimensional non-logarithmic model given by holomorphic first theory for these two holomorphic Lagrange. And so if you believe that these two answers are giving the same answer, you should get some kind of connection between BPS on the left and holomorphic curves on the right. And I will stop there. Thank you for your attention.